So what is Laplace equations? The Laplace equation is a fundamental partial differential equation in mathematical physics that describes steady state or equilibrium phenomena, situation where nothing changes with time. So we have definition here. A function's u of x, y, z satisfies the partial differential equation if the square of the delta u is equal to 0, where the square of the delta u here is called the Laplacian. So the Laplacian is of u is equal to the secant partial of u with respect to x plus the secant partial of u with respect to y plus the secant partial of u with respect to z here. So in two-dimensional, uh, the secant partial of u with respect to x plus the secant partial of u with respect to y is equal to 0. So we have the physical meaning here of the Laplace equation. It describes the equilibrium fields. No sources, no sinks here. So we have examples, temperature in the solid after long time, steady state heat flow, the electrostatic potential in charge-free region, gravitational potential in empty space, and velocity potential in incompressible irrotational fluid flow. So why it is important? Solutions are called harmonic functions. Harmonic functions are smooth, infinitely differentiable, completely determined by boundary values. So this leads to the boundary value problem, nature of Laplace equation, typical boundary value problem. The Laplacian of u is equal to 0. This is for inside a region with condition on the boundary. This is what they call the Dirichlet condition u equal to f, and the partial of u with respect to n here equal to g. This is the boundary condition on the boundary condition. This boundary condition is what we call the Neumann Newman conditions. So we have the mixed conditions. You can also include the mixed condition here. Now we have examples of the Laplacian. The u here is equal to x squared minus u squared. So the secant partial of u with respect to x equal to 2. We have the secant partial of u with respect to y is equal to negative 2. So we have the 2 minus 2 equal to 0. So the Laplacian of u here is equal to 0. So u here satisfies Laplace equations. So relate to other equations here. The meaning of u here is equilibrium, no sources. So if it is not equal to 0 and there is equal to f here, so we have sources here. Now for the heat, Laplacian is time-dependent diffusions. For the wave, Laplacian refers to the oscillatory motions. So we have the solution here. This is the core theory. We have the definition. The Laplacian v equal to 0. We have the Cartesian coordinates here. For the 2D, we have the uh, secant partial view with respect to x plus the secant partial view with respect to y equal to 0. In 3D, we have to add the secant partial view with respect to z here. So it becomes we have the three terms here. Three Laplacian, three partial derivatives here. So solutions are called harmonic functions. We have the physical meaning, very important. The Laplacian equation governs equilibrium fields. For example, heat transfer, the meaning of U here is U is steady temperature. In electrostatics, the meaning of U is electric potential. In gravity, the meaning of U is gravitational potential. In fluids, the meaning of U is velocity potential. In elasticity, the meaning of U is stress potential. So we have the key ideas: no sources, no things, no time dependence. The properties of a Laplacian equation. So we have for the mean value here. Value at a point equals to the average on any surrounding circle or sphere maximum principal. Maximum and minimum occur only on the boundary. So no interior peaks, very stable numerically. Now for the uniqueness, boundary condition determine one and only one solutions. So solving a Laplace equation in a rectangle separation of variables, for example, from 0 to L, for x from 0 to L, and for y from 0 to h. So we have the second partial view with respect to x, plus the second partial view with respect to y here is equal to 0. Then we have the boundary conditions, uh, x, x equal to 0, so u here is also equal to 0. If x equal to L, u is also equal to 0. If y here is equal to 0, so u is also equal to 0. If y equal to length is equal to h, so this becomes a function of x, f of x. So a somewhat separable form. So we have the notes here, the second partial view plus with respect to x plus the second partial view with respect to y is equal to 0. Then the x double prime here times y plus y double prime times x here is equal to 0. So divide both sides by xy. We have this expression. Transport the xy double prime over xy to the right side. Then equate both sides of then equate both sides to negative lambda. We have x double prime over x is equal to y double prime over y. Negative of y double prime over y is equal to negative lambda. So we have these expressions and solve for the x double prime here plus lambda x equal to 0. So by solving this equations, differential equations, we have the x sub n equal to sine n pi x over L. And by solving this one, so y double prime minus lambda y equal to 0. So the y sub n here is equal to hyperbolic sine in pi y over L. So the general solution here is u equal to the product of e sub n sine in pi x over L times hyperbolic sine of in pi y over L. So coefficient e sub n from Fourier sine series. So we have the explanation here. X double prime plus lambda x. So we use the boundary condition here. So for example, if x equal to 0, u is also equal to 0. If x equal to L, u is also equal to 0. So we have x of 0 equal to x of L equal to 0. So this gives a Stern Liouville problem. This non-trivial solution. Non-trivial solution exists only when this lambda is equal to the square of n pi over L. So we have n here 1 or 2 or 3. 1, 2, 3. So it is a element, and here is an element of integer, a positive integer. So corresponding eigenfunctions, uh, x of n equal to sine of n pi x over L. So this explains why sine appears. Let's give a brief reduction to Sturm Liouville problem. Sturm Liouville problem is a special type of eigenvalue problem for ordinary differential equation that appears throughout mathematical physics and engineering, especially in heat conduction, wave motion, quantum mechanics, and electromagnetism. So a general form here, Sturm Liouville problem has this form with boundary condition at x equal to a and x equal to b. We have the components here. So y of x here is the unknown functions. Then the lambda here is the eigenvalue. P of x here is the it is greater than 0. The p of x is greater than 0. This is the coefficient functions. Q of x here is the potential functions. W of x here is equal to the weight functions. So the ODE has the general solution here. So apply the boundary condition at x equal to 0. So x of 0 equal to 0. So b here is equal to 0. Since cosine of 0 is equal to 1 here. So x of x here is equal to is a sine square root of lambda times x. At x equal to L, so we have sine of the square root of lambda times L equal to 0 here. So this is also equal to 0. So this requires square root of lambda times L equal to n pi, or n equal to 1, 2, or 3, and so on. So the square root of lambda here is equal to n pi over L. So the lambda here is equal to the square of n pi over L. So we can remove a and x equal to a sine of lambda x, since substituting lambda of x equal to n pi over L into x, we have uh, x of x equal to sine n pi x over L. So n here is equal to 1, 2, 3. So we can remove a here because a is an arbitrary constant. So it can be equal to 1. And the general solution of y double prime minus k squared y equal to 0, where k here is equal to n pi over L is, so we have the general solution here. Uh, then applying the boundary conditions, y of x, y equal to 0, so it is equal to f of x, and u of x, y here is equal to h, so that's equal to g. So determine c sub n and d sub n. So solve the y here equations. So y double prime minus lambda y. So we have to substitute here. The lambda here is equal to n pi over L square of that. Then we have the general solution here. Then applying the boundary conditions, u of x, y here is equal to 0, so that is also equal to 0. So if this is equal to 0, so the d sub n is also equal to 0 here. So by applying the boundary condition, the d sub n equal to 0. So the yn now is equal to c sub n times hyperbolic of sine in pi y over L. So this explains why hyperbolic sign appears. So each separate solution is, so we have the separate solution, but we're now going to combine them. So e sub n sine in pi x over L times sine hyperbolic sine in pi y over L. So because Laplace equation is linear, we can superpose a solution here by using the summation from n equal to 1 to infinity here. So how are the coefficient e sub n found? So use the remaining boundary conditions at y equal to capital letter H. So at y equal to capital letter H here, so this becomes f of x. So our f of x here is uh, the summation of e sub n, hyperbolic sine in pi h over L times sine in pi x over L. So this is a Fourier sine series. So we have the coefficient here. So we are going to derive this e sub n. So here we have to multiply both sides by sine in pi x over L and integrate over from 0 to L. So we have this. And by orthogonality of a sine function here. So this is equal to 0 if n is not equal to m. So this is L over 2 if n is equal to m. So this becomes L over 2 here from 0 to L. Now if we have a simple explanation here, if L equal to 1, so this is equal to 1 from negative 1 to 1 here. But if it is from 0 to 1, this becomes 0.5. So we have here, if n is not equal to m, so for example, 1 is not equal to 2 here. So this becomes 0. Yeah. So solve for a sub m here. So the a sub m here is using this one. So this is our a sub n. So from this relation, we have the a sub n 2 over L, 2 over L. And we have also, we have the integral here from 0 to L of f of x sine in pi x over L. Where does this come from? So a sub n. So we have this sine, hyperbolic sine in pi h over L. So this one. So if n is equal to n here, so we have a sub n 2 over L, 2 over L hyperbolic sine of n pi h over L times this integral, if moving integral of the product of f of x and sine n pi x over L from 0 to L. So we have to recognize a Fourier sine series here. So this has the form, so f of x. So we have this b sub n here. So we make the b sub n here equal to e sub n times the hyperbolic of the n pi h over n here. So use of orthogonality of sine functions here. So we have the key identity here. So from 0 to L, we have the sine n pi x over L times sine n pi x over L. So this is equal to L over 2. We have the Kronecker delta here, nm. So this is equal to 1 if n is equal to m. So this is equal to 0 if n is not equal to m here. So we are going to multiply both sides of f of x, b sub n sine n pi x over L. So by multiply both sides by sine n pi x over L and integrate. So we have f of x sine n pi x over L. And we have the integral here of the sine n pi x times n pi x over L here. So use our orthogonality here. So this is equal to v sub n, L over 2. So this one is equal to L over 2. Here we have the canonical delta. So if m is equal to n here, so this becomes 1. So solve for b sub m here. So the b sub m here is equal to 2 over L. Then multiply this 2 over L here, this equation, then times f of x times n pi x over L dx. Now recover e sub n. So we have to recall that b sub n is equal to e sub n times hyperbolic of sine n pi h over L. So this comes from this expression here, the b sub n here. So this is our b sub n here from this expression. B sub n is equal to e sub n times hyperbolic n pi h over L. So we have the e sub n here is equal to b sub n over hyperbolic n pi h over L. So what is our b sub n here? So our b sub n here, so b sub n here equal to 2 over L times this expression. So we have this 2 over L. So we have to find first the hyperbolic sine n pi h here, this one. Then we have 2 over L. So the 2 over L here is from this one. So 2 divided by L here. So that is our b sub n. Then multiply this integral of this f of x. So we have this one. So why this works Uh, why this works? So sine functions form an orthogonal basis. Boundary geometry fixes the basis. Boundary data fixes coefficients. PDE reduces to algebra via orthogonality. So we will, it, in part two, we will discuss this properties.